So I'm Dima, I'm a PhD student at Imperial College London and Technical University of Munich, and I'm about to go join Microsoft Research, and I work primarily on machine learning for computer vision with privacy-preserving ML in place. This talk normally takes half an hour, so I have to speed through a lot of sections, and if you want to learn more, just find me afterwards. General principle, don't grill me on this, but in general, the more data we have, the better machine learning models we can train, because access to features we haven't seen before, potentially underrepresented subgroups, etc., etc. However, we can't just blindly do that. We can't ask you to donate your data, aggregate it at a central site, and then start training models. The purpose of this slide is that multiple regulations can apply within the same country as well. So GDPR is a European thing, but within the states, you have the California Consumer Act, and you have other different regulations which may apply on the state level rather than the country level. So the things which have been previously used to counter this issue, well, there are two essential ways. The first one is, instead of asking for your data directly, I can ask for it in anonymized form. So k-anonymity is one of the main ways to do it. And the second one is decentralized machine learning training. So think federated learning, swarm learning, all this kind of stuff. Just quickly, for those who don't know, FL is when you don't give me the data, but I give you the model instead. You all train a separate model, you send it back, and I now aggregate them. Even if you just average them out, it still works out pretty well. The second, however, it doesn't work. So anonymization techniques assume that there is no additional knowledge that the adversary can extract, which is never the case, because think how much we post about ourselves every day. And as a result, if you take this information, if you know something about your victim, you can very easily connect the two together and extract sensitive information from the model. Federated learning is also broken with respect to privacy, but the good thing, it wasn't designed as a privacy-preserving tool. It's a data governance tool. It actually controls who can access the data at which point, because you're the one training the model locally. Therefore, you have the governance over your own data. However, it's also subject to many attacks which are to do with privacy. So is there anything we can do about it? K-anonymity? No, we cannot fix it, because the issue of having access to a prior is something we cannot address. It just doesn't work. Federated learning, as I've already mentioned, is a good mechanism because it's not actually protecting privacy, it's protecting governance, so we can enhance it with privacy. So we want to make federated learning, or in general machine learning, trustworthy. So how do we define what trustworthy even means? And well, there are hundreds of definitions. I just picked the top 3 ones, which I normally use when writing papers, but there are actually more. And you can find different frameworks depending on which industry or academic organization you actually look into. So in this talk, we primarily talk about privacy, but don't forget, trust is also composed of fairness, explainability, and many other things which you need when training machine learning models. So I've shown this slide before. If you weren't here last year, this is what happens in a federated learning scenario when there is no privacy. I can reconstruct your data almost perfectly. This is sensitive healthcare data. Particularly, I can reconstruct the exact place where you have a tumor on your brain. Not great. And I'm going to give a more detailed overview now, and I'll potentially speed through and just talk to me afterwards if we don't have the time to go through it. To fix those issues, we introduce differential privacy. So differential privacy is a property of the algorithm. So let's pretend we train 2 models on every model on data of everyone in this room, and the second model, my data excluded. If the model is differentially private, they're roughly the same. You can't tell which one's which. It's a method which gets used a lot because it doesn't care what data you have, what model you have, what other constraints you have in place. It's really stupid simple. It bounds the amount of information that the model learns, and more importantly, you can actually quantify it. You can write a number saying this model is this differentially private. This is the mathematical formulation of how the guarantee gets calculated. In very crude terms, if you just look at the left and right hand side, it's the same thing. It's the data set with and without my data record, with some distance between the 2 distributions of data outputs. And in general, we try to use a privacy budget, so the letter epsilon in there between 1 and 10. You can have more, and if you have more, it's less private. So the higher the epsilon, the less private the model is. This is a very, very simple example. So this doesn't have to work in machine learning specifically. DP is a property which applies to anything. This is just a statistical query DP. So instead of reporting the age and the height and the weight directly, we add a little bit of noise. So differential privacy works because instead of releasing the output on its own, we add a little bit of noise to it. And the biggest problem is actually knowing what is the little bit. The amount of noise that needs to be added is super, super non-trivial, particularly when it comes to AI and machine learning models. So the way we know how much noise to add is we need to calculate how much can an individual influence the, the output of the algorithm. We can't do that in deep learning or, or AI in general, because the models are highly nonlinear, they're very big, we don't know what happens even if we change a single pixel, let alone add a single individual to the data set. As a result, the community proposed something called DPSGD, so SGD, your typical stochastic gradient descent, and it's the noised formulation of that. So this is just for a few seconds, you can look at it. In simple terms, the algorithm is the same, but instead of just doing the SGD step, when you do backward propagation, you take the gradient with respect to each individual, you clip them, i.e. you set them to the maximum norm that you've predefined, and you add a little bit of noise to that. That is more than enough to defeat almost all attacks, but the question is still how much noise do you need to add, but more importantly, why does this work? So DPSGD, because it clips and noises, obviously introduces a lot of bias. Oh God, I'm running out of time. And because it introduces bias, it's not the algorithm of choice for many settings, particularly when we talk about underrepresented populations. So this is a slide I don't have to talk about much, because you can see that people with lighter skin are in general more favored by privacy-preserving mechanisms, whereas people with darker skin actually get harmed a lot more by this clipping and noising. And most importantly, why does this happen? And we'll discuss this maybe tomorrow or later today, but it happens because not each sample that gets consumed by the model is equally beneficial, equally memorizable, and it produces the equal amount of weight on the output of the model. So this is the slide that I definitely want you to look at, which says that the machine learning, where the learning is a combination of memorization and generalization. These are not opposites. These are two processes that happen simultaneously, and this is a combination of the two. And the TLDR, because we're running out of time, memorization has to happen for a good model to work well, because some data is just not very well represented. So some of the underrepresented data has to be memorized, otherwise the model is trash. Generalization also has to happen on the side, and the point is that this is the combination of the two things which needs to happen. And we can discuss later how they get calculated. The way that we measure it is obviously also very dependent on the data set, on the modality, on the model, etc., etc. Do we measure the worst case, the best case, the average case? Same can be said about memorization and generalization alike. It's very typical. People say we don't want our data to be memorized. Not really the case. Memorization is good to a certain extent, and it's only good when these three things. It's supposed to be ABC. When these three things actually work out well, so when generalization also happens, when you memorize samples of high value, and unless you memorize them, you're going to forget them, and the model is not going to be good for underrepresented populations. And this is how we measure it. This is the formula. We can talk about that later. This is a fancy diagram we made about this specific formula. One very small comment is that highly memorized samples are not necessarily of high information content. Sometimes they're just bad, mislabeled, etc., etc. So you need to pay attention to what you're actually memorizing. This is what we did, and this is a large combination of things which I used to measure it. If you combine them, you can get a good estimate of what gets memorized or what doesn't get memorized, but in general, there is no consensus. And the conclusions are pretty bad. Again, 1, 1, 1. I don't know why that happened. There are many ways to measure it. There is no easy way and computationally cheap way to do it, and there is no unified perspective of what it actually implies when the data gets memorized. That's it.
Oh.
That was definitely not 10 minutes.
Our presentation here in 7 minutes. Okay, one quick question.
Yeah. Thank you for highlighting the difficulty in evaluating memorization and the way kind of naive privacy solutions might not actually be the solution we care about. The really crude reading from the first half of your talk will be differential privacy might be a dead end of some sort. What do you say to that?
It is a dead end if you don't know how to use it. In general, my counterintuitive opinion, because I've spent close to 3 years working on this, I think we've reached the limit of how good differential privacy can be. We're not going to get a much better formulation. Better accounting isn't going to bring us any further in terms of how much utility we can save. It is a trade-off. We have to trade privacy for utility or vice versa. There is no optimized solution. I don't think DP is the way if you want to deploy, let's say, melanoma screening machine learning algorithm in clinics, because obviously someone is going to be downplayed because of clipping and noising. But if you find a good niche for application, DP is, in 95% of the cases, is a wonderful thing to use. It's just when it comes to machine learning and privacy-preserving machine learning, it does come with a trade-off which prohibits, its use in many, particularly clinical settings. But yes, I agree. Even though I've spent 3 years doing this, I would not recommend using differential privacy everywhere as the means of privacy. There are specific use cases when it works, and there are specific use cases when you should use something else.
Thank you so much.